Go ahead, guess.
Is it interesting that they were looking at caffeine lowering the heart rate in the first place?
This is why you're reading it. Cassie has nailed the interesting part of this study. They gave caffeine to people. Who in particular is the population we're studying here? Say that again?
Males.
Good. Be more specific. I love that, Rach.
Non-caffeine drinking males.
Be even more specific. I love it. I love it. Non-caffeine using males. Oh wait, it might not say it in here. Hang on, time out. 9 male subjects. No, it doesn't. Sorry, I stripped down this study greatly. There are 9 competitive male cyclists.
Oh.
I stripped that part out, I apologize. I tried to break this down as little as I can to be as easy to read as possible. Yes, so it's 9 males, non-habitual caffeine users. So we'll just go with that. Perfect. You guys nailed the population. Okay, and my next question, Dorothy just answered, who the hell would care about this? Well, hopefully you got, once you read through it, you're like, why are they testing him on a bike? Oh wait, those guys care about it. You know, these are the guys that aren't trying to dope, I'm assuming they're trying to like get drugs legally, like caffeine. Okay, so, comment on the study. There's a lot of terms in here. Lots of terms in here. But the 3 big ones are rest, submaximal exercise, and maximal exercise. So, you see how they defined at rest? They defined it, where was it in there? Warm-up period, and then a steady state power output of 60 watts. Essentially, that's kind of like that's a moderate little pace. So you can imagine, or 60 RPM, excuse me, to get 30 watts or 60 watts, whatever it was. So you're staying well below their lactic threshold, well below exhaustion. You ever ride a bike so fast your legs like they're gonna fall off? That's maximal, right? That's maximal. Your lactic acid's burning, you can't spin anymore, and that's when they stop the exercise. Well, these guys couldn't maintain their pedal cadence anymore. Everybody's felt like that from time to time on the bike. So rest is well below that. Sub-maximal, they've defined to be a certain range below that max limit, and then maximal when they're going all out. And what's interesting is, they were checking caffeine. They were checking caffeine to see what caffeine would do. Now, what do you think caffeine would do?
You'd think it would increase your heart rate.
It makes perfect sense that caffeine would increase heart rate. Or, if nothing else, do nothing to heart rate. But the last thing you'd expect caffeine to do is lower it. And if you read the results part of this, I think I have it in here. Yeah. If you read the results part of it, caffeine didn't lower heart rate all the time in this study, did it? It didn't lower heart rate all the time. It didn't lower it at rest, and it didn't lower it during maximal exercise. But it did lower it during what they're calling submaximal exercise, which is the title of the article. Low doses of caffeine reduce heart rate during submaximal cycle ergometry, which of course is a lot of words. And most of you don't care about that, and that's okay, because most of you are competitive road cyclists who don't care about this kind of thing. But when you're a competitive road cyclist and the margin for victory in a quick stage race is sometimes seconds, that might make all the difference. Keeping your heart rate lower, keep your energy up for a longer period of time, keep that VO2 max level optimized. So see what I'm getting at with this? Every little tiny advantage helps. Some of those are mechanical advantages, making the bike lighter, making yourself more aero, and some of them are just making sure you can abuse yourself more efficiently than the next guy or girl. Cool? This is what I want to talk about a lot today. These are the big guys. Those are the big guys. I want to make sure we walk out of here today with a really good understanding of that. Okay. Now, I asked you a couple things informally. For example, I said, what would you think caffeine would do to heart rate? To which Cassie immediately said,
Lower.
what would you think though, before you read this report?
Oh, it would increase it.
You would think it would raise heart rate, or at least not lower it. That's what you would assume. Caffeine's a stimulant. Being a stimulant, you would assume that it wouldn't lower heart rate, that it would probably do exactly the opposite of that. When you go into a study, that's called the null hypothesis, the status quo, if you will. The status quo, the null hypothesis says, why would I expect anything different than what has always been demonstrated? Caffeine is a stimulant. Caffeine raises heart rate. It's always demonstrated raising heart rate. So therefore, if I take caffeine, caffeine is not going to lower heart rate. Why would it? Why would it? What's the opposite of does not lower heart rate? That's kind of a stupid question.
Lowers heart rate.
That it lowers heart rate, thank you. As soon as I said that, I'm like, oh my god. It is 9 o'clock in the morning, but that's even easy for 9 o'clock in the morning. The opposite is that it lowers heart rate. That's called the research hypothesis. You mentioned that earlier, Rosie. That's the research hypothesis. One of these two things is correct, on average. Now, different people, different things, right? Different people, different things. People act differently. We're talking about averages here. On average, one of these two things is going to be correct. The problem, we don't know which one is correct. And we'll never know with certainty which one is correct. So what we do is we set up what's called a hypothesis test to try to discern, to try to get from data which one appears to be correct on average with 95% confidence. With me so far? That's the whole idea. You have a research hypothesis you want to test. You're testing it against the null hypothesis, which is what's already commonly accepted. And this is the tool you use. Let's take a step back here for a second. Why would this even be, why would you go into, this is a non-statistical question. Why would they even test this? Who would think in their right mind that caffeine would lower heart rate? Do you think somebody just woke up one day and said, oh my God, you know what, I think caffeine lowers maximal heart rate during exercise?
Maybe they were just trying to find something to help fight breakers.
Yes, absolutely. We're just trying to find some legal advantage to aid elite bike racers to have that little tiny advantage. I often hear stuff like this get touted around my old mountain bike rides. I used to mountain bike a lot more before we had Max. And people would always say things like, you know, circus peanuts do the same thing as energy bars. Which I was told on April 1st, 1998, and I totally fell for it. I went to the store and bought a whole bunch of them. I ate them for like 3 months. I'm like, you're totally right. These are just as good as Cliff Bars. And then I realized it was like for Fool's Day. But that's the idea. I can almost see a bunch of road bikers sitting around Starbucks or Bellataz after a road ride and saying, you know what, dude? If I drink a little bit of this before we go out, right before those hill climbs, I actually feel like I get a second wind. And if enough people start saying something like that, you can say, you know what? This might have some legitimacy to it. It doesn't work for just one person. Just one person can be like a circus peanut. But if like 2 and 3 people are going, you know what, dude, you're right. It's not, I don't think it's in my head. I think I'm actually getting better legs on climbs. Then we can actually set a test up to test to see if it actually has some merit. Maybe it does, maybe it doesn't. As you can see from this report, it does it in every case. It does it when you're going all out, and it does it when you're just spinning. But somewhere in the middle, it appears to lower it. Good. That's the whole point. Now, I don't want to get into the actual test today. The test they ran, I don't want to get into that. Although, if you had to pick a Z or a T test, what do you think kind of test they used? And they could have used something different besides a Z or a T. There are thousands of tests out there. You know, hundreds, I guess. What do you think they used? If they're measuring heart rate, what do you think? And you could go, T, how come T?
Measurement.
Oh, because we're measuring heart rate. Good, good. Beats per? Beats per minute. Usually is how heart rate's measured. Beats per minute. Minute is a continuous time, therefore it's continuous. Anybody say Z because it's beats, counted beats per minute? No, I think a T-test is illogical because you're averaging. Even if it's discrete, you're still having an average heart rate. So I believe that would be a T-test or some derivation of an average test, which the whole back part of this course is about anyway. We good so far? So we have a hypothesis that we want to test. In words, here it is up here. Here's the one we're testing against, which is the status quo. This is going to be the tool to decide. And just so you know, starting next week, this is all we do the rest of the course, is develop these things. See which kinds of tests we have to run in which situations. But before we go any further, the reason you have this section, the reason I created this, the reason I just gave you all these PowerPoint slides, textbooks don't have this section. This is interpreting what's called the p-value, which goes right back to that rare event rule. I learned years ago that students have a hell of a time learning both the hypothesis tests and the p-value at the same time. So it makes more sense to stop and talk about this first, then get into the actual tests. All right, here is a snippet from the methods. Actually, that's a conclusion, excuse me. Caffeine, significantly lower heart rate compared to placebo. I think we've heard these phrases before, at least the phrase placebo before. What's placebo?
It's a pill with nothing in it.
That's exactly, for a drug, yes. For a drug, it's going to be a pill with nothing in it. Sometimes they call them sugar pills.
Yeah.
Yeah, it's a pill that looks exactly like every other pill in the experiment. It's indistinguishable by the eye. And hopefully, if it's a double-blinded study, it's indistinguishable by the researcher that's handing the pill to the subject. The only person that knows is the person behind the screen that has a label of them, and they one by one they hand them out. Who gets them? The experimental group or the control group? Who gets the placebo?
Control group.
The control group gets the placebo. They're controlling the experiment. What are they controlling? When they talk about the control group, what's being controlled?
Well, they're making sure that it's actually having an effect. The pill that they're giving them is actually having an effect rather than anything else.
That's what they're controlling, everything else. Or at least they're trying to control everything else. When they say control, you're controlling every other variable that might be affecting the heart rate. Now, you can't do this perfectly, generally, except in an ideal case, which doesn't exist. So the best you can do is try to minimize the effect of other variables that might be getting in the way. For example, stress. For example, a researcher that knows what they're going to get. I mean, imagine researchers all going to go, here you go. And then walking back out. I mean, imagine that. Like, okay, let's get on the bike. But no, there's a pill. There's a pill. That's why I tried to control for that experiment on Tuesday, when you guys were doing the which hand do you feel. I tried to get y'all to say the same thing. Above which of your hands is my hand? Above which of your hands is my hand? Trying to control for any inconsistency. Feel me now? How about now? Like, that's what I'm trying not to do, is allow whole inconsistencies like that to happen. Fair so far? Good. Oh, the experimental group's the other group. Sorry, I jumped right over that. The experimental group's just the other one that gets the caffeine, or whatever drug, or whatever treatment, or whatever diet, or whatever change is being indicated. Okay, now, here's the deal. This is conversational, but I want to make sure that you get this. Remember that geometric proof I did for you on Tuesday? I think a few of you vomited after I did it. I had to prove, or I wanted to prove, that when I threw the discus, it flew off at a right angle. What did I start by assuming? You remember? Well, can I phrase that differently? Is that okay, Chris? I like what Chris said. He said it's supposed to go straight. I'm going to make it more general, if that's okay. Not that it's supposed to go straight, but it's not going to fly off at a right angle. Is that fair? Now, going straight is one of those very large categories of it's not going to fly off at a right angle. If I say it's not going to be a right angle, then I've covered every possibility. That's called assuming the null. So in other words, even if you think caffeine lowers heart rate, you're going to go into the experiment assuming that it does not. That's assuming the null. The null hypothesis is the opposite of what you're trying to prove. So you go into the experiment assuming the opposite of what you're trying to prove. And then hopefully you get what's called a contradiction. And a contradiction is what we're going to develop today. That contradiction idea. The rare event comes in. That's the whole point. A contradiction is the rare event happening. So what you do is you go in assuming caffeine is doing nothing. Then you're pleasantly surprised when you get the data back and it appears that caffeine actually does something. And then you go, oh, I assumed caffeine wasn't going to do anything, but look what just happened. Therefore, caffeine must do something. You see what I'm getting at? It seems a little ass backwards, but there's a reason we do that, and we'll come back to why. All right. This is how we make our decision. These little p's, notice how they're capital. Your textbook makes them lowercase, your TI makes them lowercase. This pisses me off with a capital P. There are so many little p's in statistics. Little p hat. The probability, very often in your textbook, is a little tiny p. Whenever it talks about a p-value, I'm going to use a capital P, because I want you to differentiate between little p, which is what? What's little p? Little p. Population, proportion. What's little p hat? Sample portion of the population, good. Capital P has nothing to do with a proportion. It's a probability, which technically is a ratio, but it's a probability. Now this looks weird. This looks weird because it's conditional. Remember him? Nice. Give it. What's the chance that you get the data in your experiment assuming your null hypothesis is true? So you go into your experiment assuming your null hypothesis. I'm going into that experiment assuming that caffeine has no effect whatsoever on heart rate lowering. What is the chance that I actually got lowered heart rate? Do you see how those two halves of that probability are opposing each other? You go into the experiment assuming caffeine has no effect, but the data comes back and shows what? That it has an effect. So you're assuming it's not going to have an effect, but it has an effect on the data. What do we call that? Starts with, we call it contradiction. That's a contradiction. That's what you're looking for in a research study. You're looking for the contradiction. Some of you might not understand why we're looking for a contradiction. It seems like we're going around the corner, we can just go straight through. There's a reason. It's a mathematical, it's more graphical than mathematical. We're going to get to graphs pretty soon. But that's the idea. That's the idea. Let me see where we're headed here. Let's look at, no, let's not. Let's take 5. I'm seeing a lot of yawning, a lot of glaze. Let's take 5 before we get into the graphs, because the graphs explain everything perfectly, but if you're glazed and yawning, the graphs are going to be lost on you. Go, walk around, get water, get air. Get out of this room momentarily. Captain talk. Turn the camera off too.